Welcome, everyone. We are talking about force analysis, in particular for a single system. And there is a set of useful steps that you can fold in to your usual problem-solving process. In the understanding phase, you want to make sure to identify clearly what your system is. And for representation, you almost always want to choose a free body diagram to represent your forces. While you're calculating, you want to think carefully about whether your acceleration is 0 or not, and then use the law of motion. And lastly, in sense making, you can try out a thing called special case analysis. So the practice example problem that we are going to do today is that a skateboarder on flat level ground is being pulled forward by an angled kite. And we are going to go through all of the regular steps that we use when we're approaching a real world context, in addition to the steps that you see here. So we'll start by identifying a system. I have a skateboarder here, so I'm imagining that the system might be my skateboarder. That's probably not the only system that I could choose to solve a problem like this one, but I think it's a pretty good one for starting out. So the system is going to be my skateboarder, and then I want to make sure that I have a good handle on all the different quantities that might be interesting here. I'm going to assume the mass of my skateboarder is about 50 kilograms. That seems pretty reasonable. I looked up forces on kites and found that the force in the string, the tension force in the string of a kite, can be anywhere between about 50 to 100 newtons, depending, of course, on the wind and all sorts of other things. So I'll pick an easy one for us and pick 100 newtons for the tension in the kite. And of course, I know that the gravitational constant is 10 meters per second squared. I'll probably need that number today. That's probably good for now. Oh, the thing I'm going to be looking for is the acceleration of the skateboarder. Since I'm being pulled across flat level ground, I'm not expecting any friction, which means I should be accelerating. So next, I might think about other assumptions here. Obviously, I'm going to be near the surface of the Earth. I'm going to treat the skateboarder as a particle. I'm going to ignore air resistance or friction or anything like that. That's a decent list of assumptions for now. Again, we can always circle back and add to that later in the problem. All right, now we have a big new step here, drawing a free body diagram, which is a new kind of representation. For the free body diagram, if you remember, you always want to represent your object as a small box or dot, something like that. I'm going to pick a regular sort of Cartesian up, down, left, right coordinate system, which I'll draw off to the side. You can also draw that on top of your free body diagram, but I like to put it over to the side unless I have a good reason otherwise. And then I need to draw some forces on the skateboarder. I'm definitely going to have a gravitational force. Label that as the gravitational force. Let's see. I like to do on the skateboarder by the Earth. Another force that I might have is the force from the kite, from the rope, rather, that the kite is connected to. I'm going to go ahead and assume that I am being accelerated to the right, which is the positive x direction. So the kite force is pointing off at some angle like that, which again, I should label this force. This would be the force of tension on the skateboarder by, let's call it the kite, just so that I don't have too many S's floating around for string. And then it looks like I might need a normal force on the skateboarder by the ground. That's probably going to be on the smaller side, so normal force on the skateboarder by the ground. And just sort of eyeballing my free body diagram, I very quickly noticed I probably need this gravitational force to be a little bit bigger because I'm not expecting to be accelerating vertically here. So I have finished the understanding part of the problem, so I can move on to calculating. The first thing that I can talk about is the acceleration, 0 or not 0. I already mentioned this. I'm expecting it to be 0 vertically, because I'm not accelerating through the ground or up off the ground, but not 0 horizontally, which means I have a dynamics situation. So when I go to write down the law of motion, which says that F net is equal to m times a. That a is not 0. In fact, it is the thing that I'm looking for here. And one thing that I'm quickly noticing here is that I didn't define the angle at which the kite was pulling me. So I'll go quickly add that back to my picture. Maybe I'll pick a different color here. So I'll say this angle here is theta. And I'm going to go ahead and say that I know that angle. So I'll add it to my list of known things. And just eyeballing the picture, let's say it's 70 degrees. All right, so back to calculating. I have the law of motion. I'm going to go ahead and use it. One thing that we always know is that the law of motion is a vector equation. In fact, let me add my little vector symbols here, which means it's really a collection of equations, one for the x direction, one for the y direction, and even possibly one for the z direction. So I could then further break this out into an x and a y version of the law of motion. In the x direction, which is horizontal, I actually only have the horizontal component of the tension force. And you'll notice that unless I really need to keep them all, I might drop some of the symbols here, right? It doesn't matter for my equation reasoning that all of these are acted on the skateboarder, but it's really good to have on your free body diagram to keep track of. So that's the only force going on here. And that's going to be equal to the mass times the acceleration in the x direction, which is the whole acceleration. And then in the y direction, I have a tension in the y plus the entire normal force minus the gravitational force, because it's going to point downwards. And that's going to be equal to MAY, which for us is 0. So now I have my laws of motion written in the x and y direction. If my objective is to figure out the acceleration up here, it looks like the x direction is going to be more helpful. Sometimes you need both equations, like you'll need to solve the y equation for something and then plug it into the x equation. But this one looks straightforward enough that I think I'm going to be able to get away with just the x direction. So let's go ahead and take that here. So looking just at the x direction, I can see that using a little bit of trigonometry, I get ft cosine of theta is equal to m times a. That's pretty easy to solve for a. I get ft cosine theta divided by the mass. And then, of course, I can plug in the numbers that I chose, and I get an a that's approximately equal to 0.75. You can go check those with a calculator if you want an even more precise value for the acceleration. And you might have picked different numbers, in which case you'd get a different numerical answer than me, but you probably would have the same symbolic answer. All right, last of all, I can do some sense making here. First, I might want to check that my units are right. I can see that I've got newtons in the numerator. I've got kilograms in the denominator, and I know newtons are kilogram meters per second squared. So this already has meters per second squared, which is great for acceleration. I do have a cosine theta in here, which might make you nervous, but one thing to remember is that the cosine and really any special function is unitless. So I'm not going to have any trouble there. So newtons over kilograms, meters per second squared. Looks like I'm in great shape from the units perspective. I can also check numbers, and you'll note that I forgot to put my units on the number here, so let me quickly add it. So I got 0.75 meters per second squared. I might want to think about how that fits into my context for other accelerations. A really common one is g, which I have written down. G, which I have written down, but I didn't need to use actually, which is 10 meters per second squared. And I know that that's a pretty big acceleration as everyday accelerations go. But as someone who might imagine being on a skateboard pulled by a kite, I sort of expect this to be quite a bit smaller than that. When I look at the number 0.75, it's actually less than 10% as big as the acceleration due to gravity. So this seems like a pretty sensible number. I'd be really concerned if I'd gotten, 10 or 11 or even something bigger than that. Lastly, I can try to make sense of the symbolic answer itself. One way that I recommend using is called special case analysis, which you'll actually see in a future section. For now, I'll do that by exploring what's going on with the cosine theta piece here, which is where you would focus special case analysis once you've mastered it. So the cosine, if you remember, is a function that starts really high at theta equals 0. And then when theta gets to 90 degrees, it goes down to 1. And so the qualitative behavior is that cosine decreases as theta increases. So then I can go over to my picture here and think about what that might mean. Well, a theta, which is really small, let me move some of these forces out of the way. A theta, which is really small, would correspond to the kite pulling me in this direction, which does look like it would give me a bigger acceleration because all of the tension would point forwards. On the other hand, if I made theta big, close to 90 degrees, I'm going to get that not very much acceleration happens. And then you can see that that pretty much changes smoothly as I go from theta equals 0 to theta equals 90.